All right, so we were faster than I thought. Ladies and gentlemen, Arushi Nath, take it away.
Thank you very much. It's great to be presenting here at the Toronto Center once again. My name is Arushi, and I'm a grade 10 student. And today I'll be talking about using n-body simulations to analyze transit timing variations in exoplanetary systems with multiple planets. So let's get started. So first, what is an exoplanet? Exoplanets are simply planets who orbit stars outside of our solar system. So let's look at a simple GIF of an exoplanet right now. Here you can see the exoplanet is orbiting around its host star because of their mutual gravitation. You will notice that as the planet goes in front of the star, a small portion of the star's light is blocked, creating a dip in its light curve. And the planet will go and transit once again, and the dip will be observed once again. An interesting thing is in a single planet system, the planet's orbital period is constant, which means after a set amount of time, the dip will happen once again, and we'll be able to predict when this dip would happen. But let's say we make it a bit more complicated. What happens if there's multiple planets in the system? Let me play this GIF here. So now you can see there's multiple planets. And now there's not only the gravitational interaction between the star and the planet, but also in between the planets itself. And this creates shifts in the orbital period. Let's look at these figures. Let's look at the inner planet, which is orbiting. It's getting pulled towards the outer planet, meaning that the known planet will be sped up a bit. And this means that the transit will occur earlier. The opposite can happen too. Let's look at the figure below. Here you can see the inner planet is orbiting and the outer planet is behind it. Because of their mutual gravitation, the inner planet will be pulled towards the outer planet, and this will make this planet slow down a bit, causing the transit to happen later than expected, which means that transit shifts can be observed between transits, meaning that the planet's orbital period is not constant. So, what would happen if we plotted this orbital period each time? Look at this curve right here. Here, I've plotted the light curve of the transit for 9 different orbital periods of the planet. You can see that there are slight variations. In the start, it happens right at the center. You can see that here's the mid-transit. But in the second epoch, you can see that the mid-transit shifted a bit towards the right. And for reference, the blue line, vertical line right here, is the predicted mid-transit time of the exoplanet. So, what can we find out from these curves? Well, let's say first epoch 1 is normal. We can see that the mid-transit time happens exactly where predicted. Now let's look at the second orbit. Here, the second orbit happens a bit later than predicted. Same for the third and fourth. And then suddenly it's happening earlier because of the mutual gravitational pull between other planets. So, what happens if we subtract the observed mid transit time and the calculated mid transit time? Then we can create what's called O minus C plots or observed minus calculated plots. So here you can see epoch 1, observed and calculated were the same, so it's 0. Epoch 2 happened later, which means the observed minus calculated is positive. And I've done the same for all of the 9 orbits. And you can see it produces a curve. So now let's look at an O minus C plot of an actual known exoplanet, Kepler 9. And here we can see the O minus C plot of 2 of its planets, Kepler 9b and Kepler 9c. You can see there's a trend you can see, which is very periodic. The orbital period of Kepler 9b varies by about 45 minutes during these observations, and the orbital period of Kepler 9c varies by a lot more, by about 140 minutes. What happens if we combine these two curves together? Here, one thing you will notice straight away is that both Kepler 9b and Kepler 9p display really out of phase behavior. This means that they're basically doing the opposite. While one is going up, the other curve is going down. And this is actually what we should be expecting. And the reason for this is because the mutual gravitation between the two planets, as they're pulling towards each other, one will slow down and one will speed up, meaning that one will come will orbit earlier than expected, one will orbit later than expected. You'll also notice if you look at the y-axis, it's a big transit time. The observed miles calculated has a very big difference. It goes from about 25 to minus 25 for planet B, and it goes from like 60 to minus 80 for planet C. And this strong signal is because of their near resonance orbits, which means for every two orbits the planet B makes, the planet C completes one orbit. And this really demonstrates how looking at the observed minus calculated plots, also called transit timing variations, can confirm the presence of multiple planets. Actually, Kepler 9b and C were the first exoplanets for which TTVs were detected in 2010. So, what is the significance of measuring transit timing variations? Well, there's three main points. First, using this, you can validate the presence of known exoplanets, as we saw right before with Kepler 9b and C. Simply by looking at their transit timing variation plots, you will definitely notice that there has to be another planet. Second, it can also reveal the presence of additional exoplanet. If you only saw one of those TTV curves, you would note that there's likelihood another planet in the system, which can reveal a multiplanetary system. Third, as you might have remembered before, I said that these TTVs are caused because of the gravitational pull between planets, which means that by observing these transit timing variation curves, and by looking at their shape, by their amplitude, we'll be able to determine planetary masses and orbital characteristics of both planets. And this technique is really powerful because it can reveal properties of exoplanets that don't even transit the star. So far, we have been able to detect 32 new exoplanets through transit timing variations. But there's a few challenges with transit timing variation analysis. First, there's a lot of noise. And because when we're looking at these TTV curves, this is all based on the mid-transit timing of the observation. This means that when observing the mid-transit time, we need really precise observations. But there's always instrument noise, sometimes there's multiple stars, sometimes there's calibration errors, and all of these errors can add up, and we have to make sure we don't confuse these errors with the TTV signal. Second is obviously observational constraints. Because limited transit events for long period planets are possible, because they only orbit, let's say, every 100 days, 200 days, which means we might not have enough observations. In addition, sometimes telescopes can only take observations every 10 minutes, 30 minutes, and let's say the period of the exoplanet is really small. That means that there could be some gaps in the data, and this can produce a few errors in the measurement of the mid transit time. Third, and a very important point, is degeneracy. Because these CDV signals are based on the orbital parameters of the planet, it's important to note that similar TTV signals can be produced from different planetary configurations, as we'll see a bit later, and this can really complicate the interpretation of mid-transit timing variations. Finally, there's multiple effects that can cause variations in the transit time, including orbital decay and light time travel time, and we have to make sure we do not confuse these with transit timing variations. Luckily, TTVs, because of multiplanetary systems, have very short periods compared to orbital decay, meaning that we can distinguish between them. But it's also very important that we learn to subtract the orbital decay from the curve. So let's look at degeneracy. Here you can see the plot of two different planet systems. In the first one, you can see the mass is more and the centricity is less, 0. In the second plot, you can see the mass is much less, but the eccentricity is more. But you'll notice that these produce near identical transit timing variation plots. This means basically mass and eccentricity produce very similar signals in TTV plots, making it difficult to determine which one is causing the signal. Or maybe it's a combination. There's also other degeneracies, for example, with mass and orbital distance, and eccentricity and inclination. So my project had three main goals. First, generate thousands of n-body simulations that accurately model these gravitational interactions between planets in multiplanetary systems. Second, train machine learning models on these synthetic um, data from the N-body simulations and validate their performance using data of real exoplanets to identify these TDV signals caused by the planets and find their properties. Third, use the machine learning model and other techniques to break the genesis in, parameters to be able to accurately determine all of the orbital parameters of the exoplanetary system. So here is a quick look at my methodology. So first, I'm creating n-body simulations, which is really important. And this is done by varying the orbital parameters. Second, I'm using real data from um, the 32 known TDVs to be able to determine the parameters for the n-body simulations. Third, I'm creating thousands of n-body simulations to be able to train my machine learning model on. And fourth and fifth is still ongoing, but creating a testing set for machine learning model and identifying significant transit timing variation for further analysis. So first, generating the synthetic TdV curves. So here I use 7 parameters. I use the mass of the planet as well as the 6 orbital parameters. So the mass, the orbital period or 7 major axis, eccentricity, inclination, longitude of ascending node, argument of perastron, and mean anomaly. And all of these have different roles in the creation of the TdV curve. So here is the algorithm that I used to generate n-body simulations. So it's based on both nbody.ai and Rebound. And you can see a sample of my code here. And using this code, I'm able to generate an n-body simulation as you can see here, which is basically an O minus C curve. Second, parameter optimization. And this is really important because we want our bounds when creating n-body simulations to be realistic and match with real data. So to do this, I set up constraints based on the current 32 TDP detections taken from the NASA Exoplanet Archive. And based on this, I was able to create ranges for the planetary mass, orbital period, eccentricity, inclination, and argument of perastron, which I fed into my n-body simulations to make the data realistic. And this these n-body simulations were run on 2 planet systems. So there's the known planet, the perturbed planet, which is experiencing the transit timing variations, and there's the perturbing planet, which is causing the transit timing variations. So third, now that I had my n-body simulations running and I had all my parameters and constraints set up, now was the time to create the training set for machine learning models. So far, I've generated over 12,000 n-body simulations generated on my non-GPU computer, and these are basically to mimic realistic scenarios. In addition, 10% noise has been added to account for instrument errors, uncertainties, and a few unaccounted effects. Validation. So I was able to validate my M-body simulations to match with real data on Kepler 9b. You can see that both the O minus C curve for planet B and planet C match very well with the literature. Thank you so much. In the future, I will be making my machine learning models and I'll be creating my testing data sets using the real data. So thank you very much. I'd be happy to answer any questions.
Thank you very much, Arushi. That was a wonderful presentation. Let me just see here. Okay, so we have some questions. Um, with your Python code, have you had a chance to run without the global interpreter lock and see if there's any discrepancy with your result?
Um, Actually, no. I'm actually not too certain what the. Sorry, could you repeat that question, the first part?
Okay, so the question is, with your Python code,
Yes.
have you had a chance to run without the global interpreter lock and see if there's any discrepancy with your result?
No, I haven't experimented with the global interpreter lock at all. I'll have to read up on that, and maybe if it's something that would improve my TTV simulations, I'll definitely try that out. But thanks for pointing it.
Okay. And then the next question, Okay, so the next comment is unistellar telescopes are used to follow up exoplanets by amateurs. 3.5 inch mirror, I believe, from Zapfan.
Yes, that's true.
And then Lewis R would like to know what software are you using for your LLM?
So I'm actually not using any LLMs in my project. So far I've been creating the n-body simulations, which do not use any machine learning. In the future, I will be using neural networks to be able to use the training data of my n-body simulations and be able to predict the parameters.
Okay. And then from Pavel, is it difficult to distinguish TTV due to other planets from, for example, precession due to the star's flattening?
That's a great question. And actually, yes, because transit timing variations caused by gravitational interactions is really unique in the way that the period that this happens is really small. So it happens every few transits. You can see there's a huge difference in transit timing variation caused by the gravitational pull. And also, you will notice that TTVs are almost like sinusoidal curves. So they keep repeating each other over and over, which makes it easier to distinguish between that and other effects. But it is also really important, even if we know how to distinguish between this and, let's say, the uh, apsidal precision, it's really important to still be able to remove the effects of apsidal precision and other effects so that we can totally isolate the TTV signal due to other planets.
All right. And, oh, hold on a second. Some more questions coming in. Are people looking for moons around exoplanets using TTV?
That's a great question. And in fact, it's definitely possible to be able to look for moons. And those moons would cause a transit timing variation too, just like planets. And I believe people have tried. I'm not sure how successful they were, but it's definitely something that has been experimented on before.
Okay. How powerful a telescope is needed to detect exoplanets?
That's a great question. And honestly, it doesn't need to be very, very big or very huge telescope. And even small telescopes by amateur astronomers can be very helpful. Actually, there's several initiatives. For example, ExoClock, which is actually meant to basically build a network of amateur astronomers with small telescopes ranging from 6 inches to maybe 12 inches and 14 inches in diameter. And these are used for follow-up of exoplanet observations. And so as long as you have a telescope, you'll definitely be able to observe most exoplanets, especially since exoplanets are simply discovered by dips in measurements of a star's light. And most stars are really bright and we can observe them easily. To be able to detect an exoplanet, however, is slightly harder simply because most of the exoplanets that we have the capabilities to detect have already been detected. But even if you can detect an exoplanet with your own telescope, you can definitely help in improving the ephemerides of known exoplanets or contributing to observations of exoplanets where maybe not enough have been done. And I think that's a really important role of amateur astronomers right now.
Okay. And next question. Referring to your previous presentations, how did you get into studying exoplanets and asteroids?
Yeah, that's a great question. And honestly, I think RASC has a big part to do in it. That's where my interest and love for astronomy started. And I remember I used to be really fascinated with planets before, and then I remember looking through a huge telescope and then seeing other objects that moved, like asteroids, and it made me fascinated. And I wondered, since so many asteroids, for example, I started with asteroids. So since so many asteroids are out there and we haven't detected all of them, I became really curious on how to detect more asteroids. And then from there, I learned to basically create light curves of asteroids. And I think in the past few years, especially, I've been really interested in performing precise photometry, which is basically looking at minute change in light coming from celestial objects. So I started from asteroids, and then I think the natural path for me was exoplanets. And exoplanets, it's almost applying a similar technique because exoplanets, I'm also looking for precise changes in brightness during the transit. And so that's what I'm working on right now.
Okay. And our last question, what is the furthest exoplanet discovered to date, and what's the closest?
That's a great question. And actually, I'm not sure that's something you'll have to research on your own. I don't have the stats with me, but definitely there'll be some information. And um, over almost 6,000 exoplanets have been discovered so far. So definitely do some research, and I'm sure you'll be able to find the closest and furthest.
All right. Well, thank you very much, Arushi. That was wonderful.
Thank you
Okay.
so much for having me.